Hello everyone, my name is Etienne Reboul. I'm a PharmD PhD candidate. I work at the Laboratory of Theoretical Biochemistry in Paris under the supervision of Dr. Antoine Telly. So my talk today is going to be about ConfScale, which is a Python package that has the aim is to provide utilities to do some data formatting, conformer generation, data parallelism, and some conformer selection. The overall idea is to provide a package with utilities for downstream studies involving 3D structures such as machine learning task and deep learning task. So the pipeline is fairly simple. The overall idea is we take a raw database, we apply some data curation to create input files, we do a conformational search with RDKit, and then we apply filtering. We try to find something like a set of unique conformer, which is not a very straightforward thing to define. And then we do some data formatting for the output file. Okay, so for the data curation, when working with large database, we run into some problems such as loosely defined file format. For example, we have all see the SME files, which basically are a bunch of tab-separated column, and you have one smiles and then a number of attributes that is the other columns. And also we have the problem of sometimes the data is not well distributed in the files of the database. For example, here is an example of the Zinc20 database for the drug-like subset. And what you can see is the distribution of the data is skewed and it is not very uniform. And you have some huge files and some very small files. Also, we have little to no metadata and data types. So for example, here is the header of a SME file. You can see that you only have the column names and you don't know for sure what it is, especially the computer. Pandas can guess what it is, but you know a smile is a string, a Zinc ID is an integer, but that is not something that is straightforward for a computer. Okay, so to remedy that, I wanted to use a more standardized file format, which is the Parquet file format, which is open source. The overall idea is the Parquet file format has some nice tricks. It supports a lot of compression algorithms, such as gzip, which is most well known, and some more obscure ones like ZSD, Brotli, and Snappy. And it also has very efficient encoding for low cardinality data with redundant categorical data with dictionary encoding, byte packing, and delta encoding, but that's some obscure trick that I'm not going to detail here. The idea also is the Parquet file, because it is stored as column, can load an arbitrary number of columns, which can be very practical in some cases. For example, when you have a very large files with a lot of descriptors, such as the Draken molecular descriptors, we can go up to 5,000 approximately. It is interesting to be able to learn just a subset of that data very fast. Also, the Parquet data set has schematics which fully supports data types and metadata. So the idea here is that you can just say include in the Parquet file what your data is, what is the data type. So for example, here we have the fields, which are the column names basically, and then we have some data types that you can specify like strings or unsized integer 32. And then the description is the metadata. You can explain specifically what your columns are. It's also interoperable. So the main, I think, entry point for a Python user would be the Pandas library. And basically, Parquet, reading Parquet and writing Parquet is very simple. It is one-liner, you can see here, although you do need to install some dependency, which are PyArrow or FastPacket. So the overall idea is we take a raw database, we apply some standardization workflow like stripping souls, canonize the smiles, and then we take this curated database, we apply a user-defined schema, and then we get Parquet files. So one of the use cases is with the Zinc database, which I talked about. So basically, the uncompressed file format when you download the Smiles is roughly 47 gigabytes. And the idea here is with Dask, which is a multiprocessing framework that I'm going to talk about a little bit later. You can rescale everything. You can like repartition your data entirely, and you can go from something that is like a very skewed distribution to a more Gaussian-based distribution. And Snappy is designed to process files rapidly. So you can see it only takes 2 minutes to compute, to process roughly 50 gigabytes of data. Another use case would be, for example, the enumerated space, for example, of freedom space, which contains, for this subset, 435 millions data points. And the idea is the original compression algorithm. When we used like the original file format, it was 13.8 gigabytes. And when you do the uncompressed files, it's 60.2 gigabytes. And the overall idea is we can process that all into a uniform amount of files. And they are small and, well, relatively small and relatively well partitioned. So the overall idea is Parquet file format is good because it has data type and metadata. It also has a lot of interoperability. A lot of libraries are able to read and write Parquet files. And it's really interesting to store column data. When you have a lot of columns, you can load them independently. So that's nice. However, as you can see for the example I showed about the enumerating freedom space, the compression algorithm do not outperform a standard compression algorithm like gzip when there is high cardinality, basically because each data entry in the enumerated space is unique, then it struggles a lot more and doesn't has as much compression than what you would have with low cardinality data. Also, the problem is readability because it is a binary file and they are traditionally not readable. However, you can use extension in VS Code, for example, like Data Wrangler to see data files, so it's somewhat readable. The idea moving forward is I want to support more data type, especially for machine learning application. One thing would be nice because data Parquet format support nested data, you can think of saving one-hot encoding data. You can also save binary arrays such as fingerprints, and you can also store something like SciPy sparse matrix. Now, going to data parallelism, the idea is we want to generate a lot of conformer of different molecules. So for that, we use the ETKG3 algorithm I'm not going to present because that would be redundant from yesterday's talk. So the overall idea we want, because it is an application for drug design, we want to generate conformation that look like crystal-like. And the implementation is decently fast because it has multi-threading, and you can use optimized forestall parameters, such as the one I find on an RDKit blog post. The overall idea is, can we go bigger, for example, on the PC or in the cluster? And for that, we are using, I'm using Dask. What Dask is a parallelism framework, but is powered by JobLib, which is the same parallelization framework that uses scikit-learn. The idea is it's supposedly easy to integrate with existing NumPy and Pandas data frame codes. And also, you have easy scaling, supposedly easy scaling between laptops and HPC clusters, because you have an integration which is called Dask Job Queue that manages the queue of commonly used orchestrators such as PBS and Slurm, and also support commercial architecture with Kubernetes and Dask Gateway. So how does it work? Basically, you have a client, it sends information to the scheduler, and you have an army of workers that do the computation. Basically, the data is split into chunks, and it sends to workers we have and threads. So I'm going to do a little bit of oversimplification here. The difference between a process and a thread. So basically, a process is something that has its independent running code, and it has its own code, its own memory space. And normally it's relatively safe because if it crashes, it doesn't kill all the program. There is the thread, which is typically used by RDKit C++ implementation, which is more lightweight, more easy to set up, and it's more resource efficient because it shares comps and memory space, but it's more dangerous because it tends when it deadlocks, to crash the program completely. So the idea here is we want to combine both multiprocessing and multithreading like so. So the idea is we have the input files, the clients split the input files and set them to the workers. With the worker, we use the ETKDG implementation. The ETKDG implementation is multi-threaded. We can take advantage of that. We generate a lot of conformers, and then we gather everything into a nice database. The overall idea here is a test case with Rapaxar, which is a proteinase, which is an inhibitor, is a FDA drug approved inhibitor of a proteinase activated receptor 1. And the overall idea here you see is we can actually get some speed up. This is the computation done with a setup of 5 workers using 5 Rapaxar duplicated molecule. And the idea is we increase progressively the number of threads we give to the worker, and we can see that we actually have a speed up, a quite significant speed up of the computation for the conformer generation. So overall, Dask is good as horizontal scaling, which is basically you want to have many workers that do a small job. That's why it's really important to have data formatting, which I talked in the first part, because if you have a nicely distributed data in files, it's very easy to use Dask, whereas if you have big chunks, it's a lot harder. And it works well with Parquet file overall. What it doesn't work with is vertical scaling, usually mean like creating big workers and tasks that requires a lot of intercommunication with between workers. And also that is kind of the lie of Dask, is that supposedly it's supposed to be very easy to implement your code if you have an application that runs with Pandas and NumPy, but it actually requires quite a lot of thinking to set it up. So the perspective, what I want to do is Dask has an interface with CUDA workers, and the idea is it would be nice to have some accelerated computing, especially training of deep learning models that could be done with the Dask framework. I want also to fully integrate the current existing code with the existing RDKit Pandas tools. For example, a nice application would be the distributed pattern search. And also you could potentially use Dask with Python bindings of Vina to do darking. That will also be a nice thing to do. Then comes the filtration part. So basically for the filtration part, I don't really like the RMSD. Why? Because there's a lot of drawbacks, such as you need to have to define what is a good reference, what would be an ideal conformer to use to align every other conformer, or you could do pairwise. You could do pairwise comparison with RMSD, but that is very computationally expensive. And also, it is not clear what clear threshold, clear cutoff of RMSD value that would separate two conformers. Okay, so for that, I choose to go another way. I'm using a method developed by Jessica Brown, which presented her talk yesterday. So the idea is with ETKDG3, you can analyze a molecule, find the torsion angle, and you have information from the Cambridge structural database. You can find the pattern of the distribution of your torsion angles. And with that distribution, you can bin it, especially you can like split the different Gaussian-like distribution into different bins, and that gives you torsion states. And with those torsion states, you can label your conformers. So one of the problem, well, the difficulty more so with that approach is that you have the global and local symmetry problem. For example, you have the triethylene benzene, which is symmetrical, which has a plane of symmetry. And you can also have global symmetry like on subfigure B. And basically, you don't know necessarily know what is the good way of mapping your data. And you also have the problem of local symmetry, where, for example, on the subfigure C, you can see that for the blue part and the pink part, for the first part, it is equivalent in terms of symmetry. And so when you do this torsion angle, you actually duplicate the information because they're equivalent. So the one way they were dealing with this is using mapping, because you can map a molecule with query search. And basically, if you can map it more than once, it means you have a global symmetry. However, it doesn't perform so well with local symmetry because it's difficult to map local motif. And the idea I've come up with is when dealing with symmetry, you can use the canonical ranking algorithm. And if you don't vectorize, what actually happens is each atom that has the same environment actually gets the same indices. So with that, we can detect global symmetry, because you will have a set of unique canonical index that is lower than the number of atoms. And also we can deal with local symmetry somewhat by having same indices, same canonical indices. Okay. Yeah, sure. So the idea here is that we can transform the categorical labels from tabs to generate what somewhat sim count fingerprints. And the idea is all the torsion angle with the same canonical ranking indices that are not break for ties are aggregated. And when we have the middle bond of the torsion angle the same, we can actually discard it to prevent data duplication. So an example would be, for example, cyclohexane, which is symmetrical. When you use the ATKDG3, you can find the torsion smart. From the literature, you can derive a number of bins. So this is 3 bins. So the first bin goes from 0 to 100, 120, 120, 250, and it circles back because the angles are periodic. So the idea here is we have 6 torsion angles that are identical for the canonical ranking algorithm. And what we do is we can take the 3 bins and aggregate it. So basically, the overall idea is we have the first bin, the second bin, and the third bin. And basically, we count the number of torsion angles that falls into these bins, like so. And this allows you to select conformer basically, and you can use them to do some comparison, although the code is not implemented with similarity metrics such as 10 autocoefficient. And for now, it's just unique fingerprints that are used to do conformer selection. So what I would like to say is I don't really like RMSD because you need to define a reference pose. Doing pairwise comparison is expensive, and defining a good threshold is somewhat difficult. What I like about tabs and ConfFP is it doesn't require an alignment. It is roto-translationally independent. And we can take into account global symmetry, and we can somewhat take into account local symmetry, although sometimes it does also fails. So the overall idea is ConfScale is a Python package that provides utilities for data formatting with the Parquet file format. It also helps with distributing calculation on multiple processes, combining it with multi-threading, and also it provides some way of conformer selection using derived metric from the torsion angular bin strings. Moving forward, I would like to implement a way to put SDF files and other mol file type into Parquet to try to compress the invariant part that are found in all conformers. So basically, the position of a conformer differs, but a lot of the information remains the same, the connectivity, the atom types, so on and so forth. I would also like to integrate better with some other chemoinformatic projects, such as Sticky Fingerprint and EasyDoc. Thank you for your attention, and I would like to thank the organizer as well.
Question? Right.
Yes.
So I have a comment and a request.
Okay.
I think that DAS and Parquet are fascinating, really interesting technologies. And if there are ways that we on the RDKit side can make it easier to work with. that,
Sure. Yeah.
I would love feedback from the community, from you or from anyone in the community on the way that we can make the RDKit work better with Parquet, in particular, or DAS as well. I think that it's really useful. We just have to figure out how to make it a little bit easier so that some of the things you're doing are simpler.
Yeah. So
Can you rephrase?
Yeah, that was a lot.
should I repeat the question?
Yeah.
Okay. So the question was, how can RDKit be what would be the perspective for RDKit to improve the integration with file formats such as Parquet or for data parallelism techniques such as Task? Okay, so I think I don't know if actually it's doable because Dask is extremely picky sometimes with class, especially data format. It doesn't like the ChemMol class at all. So you wouldn't be able, for example, to do take data frame, do the moles, and then distribute it to the worker. That fails systematically. What you need to do is send string data and then create the conformers and everything inside the worker, because it really doesn't like non-standardized types of data, especially like string. So I don't know if there is like some way to make like C++ class like better at handling with like the Dask system. I don't think so.
I have a concrete answer to that, but if you have something for Parquet.
Parquet is fine, I guess. Like most of it's a very flexible format with a lot of nested structure that could work with like a lot of things we use, like fingerprints and 100 conic matrices and spice part matrix. So I think it's fine from the Parquet side. Okay, sure. Yeah.
We have this whole number.
Yeah.
How do we come up with that?
I'm so sorry. I didn't cite it properly. It's actually from the RDKit blog, which has like a post about this particular forestall parameters. Sorry.
Instead of you repeating the long thing I'm about to say, it's probably easier if I do it. Can I just have that?
Sure.
So for the thing with working with molecules in Dask, I've done some experiments with this in the past, and I think what you can do is every RDKit molecule has a 2 binary method. the RDKit molecules have a 2-binary method, and that gives you a binary string, which is a description of the molecule that can be very quickly converted back into a molecule. If you put that in your pandas data frame, it's just a byte array. You can then spread that through Dask, and each Dask worker just needs to convert that back into a molecule, which is very fast. So I think it's much easier if you're doing any of these job lib based systems where you need to send, you cannot send an RDKit type, but you can send a byte array or a string. Just call 2-binary on the molecules, you get this binary string. That can include the whole molecule, multiple conformers, everything. And then on the other side, you can construct a molecule from that very easily. And that will then solve this parallelization problem. So I think that's really the best way to approach that particular issue.